Today's joint Siemon and NVIDIA Tech Talk webinar. We're here to discuss optical cabling strategies for high-performance 400 to 800G AI deployments. I'm Brian Bond, Corporate Marketing and Communications Manager here at Siemon, and I'm thrilled to be joined by Gary Bernstein, Siemens Senior Director of Global Data Center Solutions, and Ulysses Fabre, Senior Solutions Architect at NVIDIA. As always with our Tech Talks, if you have any questions during the session, please enter them into the questions panel on the GoToWebinar interface that you should see on your screen. We'll wrap up with a Q&A session at the end to address as many of your questions as time allows. So with that, let's get started. Ulysses, over to you.
Well, thank you very much. Brian, thank you very much. So let me just do a quick introduction beyond what Brian did. Well, I'm Ulysses. I'm a Senior Solutions Architect for NVIDIA. Joined NVIDIA during the Mellanox acquisition. So I am primarily a networking specialist, working with AI Factory, specifically on the connectivity side. So the goal here today is to give you a little bit of a summary and a view of some of the connectivities and the recent changes that we've done to the AI Factory using our latest technologies like XDR. Together with Gary Bernstein from Siemens, we will cover stuff from network devices and solutions and equipment to cabling to optics. So with that, let me give you a quick agenda. Again, I will go ahead and cover some of the InfiniBand and XDR and Spectrum X Ethernet platforms and solutions, moving up to our latest and greatest. That's part of our latest XDR, AI Factory solutions. I will cover a little bit about the ConnectX and Bluefield DPUs and SuperNICs and what the differences are. You'll hear SuperNICs, but SuperNICs kind of include or kind of is an umbrella of different types of adapters, because we have our latest ConnectX 8, which we'll talk about in a couple of slides, together with the Bluefield adapters that actually make a good portion of the SuperNIC category. So after that, I'll turn it over to Gary Bernstein, who will cover some more structured cabling with optical interconnects and performance and requirements that we have worked closely and with Siemens to provide. And we also, he will talk about some reference architectures and some sample designs. With that, let's move on. I am going to go ahead and shut my screen here just a little bit so that I don't distract you all. Okay, so XDR, quantum, spectrum, Ethernet platforms, what does all that mean, right? You hear all these words and they can be confusing. Well, NVIDIA is now, we're not really designing individual components anymore like we did with Mellanox. Or I should say that NVIDIA is now focusing on full AI data center designs. The networking is a crucial component of those designs that define the type of data center. It's critical to have the right networking technologies that makes this all happen, right? The computing technologies and all optimized to deliver the framework for AI supercomputers. So for those of you who are familiar with the old Mellanox, before we got acquired by NVIDIA, we made our own ASICs for every individual component. So for our network Ethernet switches, we had an ASIC designed specifically for Ethernet. We had an InfiniBand ASIC that was designed specifically for InfiniBand. And then we had the adapters ConnectX ASICs that was designed to offload a lot of the stuff on the host side. And then we have the data processing units. What we do now is we design these components to work together so they leverage each other's resources, not only hardware, but software. And we're going to get a little bit into that. So what is this AI factory now that NVIDIA talks about all the time and sells and kind of offers? Well, it consists of, when we're talking about the connectivity and the networking, it consists of quantum InfiniBand switches, ConnectX SuperNICs, Spectrum Ethernet AI switches, Bluefield SuperNICs, and then of course the NVLink that's part of the internal of the DGX side where the GPU connects and communicates to each other internally. And then we got the Bluefield DPU. So I know there seems like some redundancy here, but we're going to go ahead and sort all that out in the next couple of slides. But before we go there, let's review a little bit because it helps to kind of get a better picture as we move into the next generation and the new generation, right? So, InfiniBand generations, what's the comparison? So here, not that we started necessarily, but we'll go ahead and point out that the Switch IB2 ASIC that we designed a while back that worked together with the ConnectX-5 kind of addressed the 100 gig market. That was the EDR InfiniBand side, and of course the 100 gig Ethernet switches that we offered then, and we offer some today. The Quantum ASIC was a new ASIC, the next generation ASIC that was designed to address the 200 gig market. The 200 gig market, was important for HDR and of course, 200 gig Ethernet. That worked, hand in hand with our ConnectX 6 because, ConnectX 6 was Gen 4 PCI. And then we moved on to the Quantum 2 with ConnectX 7, and that's, what we ship today with many of our AI factory solutions because it consists of the 400 gig NDR connectivity together with the ConnectX 7. So as we move forward today, what we build our AI factories with is either with the Quantum 2 base generation NDR switch, which is our, we'll go into those individual components in the next couple of slides. But it consists of the 400 gig NDR or the 400 gig Ethernet side, and then we have the Quantum X 800 generation. And the Quantum X 100 generation works on a 200 gig PAM SerDes, or PAM4 SerDes. We can support 400 gig with Quantum 2, but well, you do that by doubling or having a dual port of 400 gig, right? So it's PAM4 100 gig, so each lane runs at 100 gig. Whereas the new X800 generation, we have each lane running at double that speed. So that's the difference between the Quantum 2 and the X800. Those are the two major generations that we use in our AI factory and SuperPods today. And we'll get a little bit more in details in the next few slides. So let's go ahead and give you a quick summary. The NDR side, the switch itself, the Quantum 2 base switch is the QM9700. Many of you are familiar with this one because this is one we've been shipping for a while. It does have, it has 64 ports of 400 gig or 128 of 200 gig, but that's accomplished over 32 ports of OSFP cages. So each physical port has two 400 gig. So each actually physical port can do 800 gig, by doubling the 400 gig. So that's what you're familiar with, and we design many of our SuperPods with this. But moving forward, let's talk about our X800 generation or platform. So before we get into the individual components, I want to make sure that's kind of a little, some of the terms that we use might be confusing because they're used interchangeably with other terms, So when you see the Quantum X800, that term, what you hear is it's an overall end-to-end solution. It's a platform, okay? And that platform or the end-to-end solution has components to it. So in this particular slide, you'll see the X800 switches, and we'll get into the different types of switches available. And then you have the SuperNICs that kind of work hand in hand with the switch, all right? So the SuperNICs in this case is the ConnectX 8. The ConnectX 8 is a 200 gig SerDes type, along with our switches, that can actually do 800 gigs. And now, because we can do that and we can double those lanes, we can actually have each port do double 800 gigs, so 1600 gigs. But we're going to go ahead and talk a little bit about that next slide. So I just wanted to kind of clear up what the Quantum X800 InfiniBand platform, which is end-to-end solution, is. Now, within that platform, we have the Quantum X800 Q3400, okay? This is our 4U box that has 72 OSFP cages, each supporting 200 gig ports. So each cage is essentially 800 gigs, double, two of those 800 gigs per cage. So this allows us to have 144 ports of 800 gigs. All right. With this, we can actually build quite a cluster, and we'll get a little bit into that. And I think my colleague buddy here, Gary, will have a couple of slides that may show a few designs later on. But just to kind of lay out the foundation here, this 4U box is the true 800 gig, 200 gig per lane. So this is the best solutions for HPC and AI workloads, supporting sharp adaptive routing, telemetry-based congestion control, and advanced power features too. It has, power capping and low power state transitions to decrease power consumption during like idle periods. So, if ports are not being used, we'll not necessarily shut them down, but reduce the power, redirect power. We really have a dynamic system there to be able to save power in here. All right, so let's move to the next one. So now within the Quantum X800 platform / system, we have the 2U box here. This is the Q3200. Okay, the Q3200 has two independent 36 port switches, side by side. So you'll see, switch one on the left and switch two on the right. That supports again 800 gigs, dual 200 gig port per cage, right? So that's 36 ports of 800 gig per side, for a total of 7,200 or 72 800 gig ports for both sides. Now, this platform is really made and designed to be backwards compatible. We'll be able to plug in NDR and HDR technologies to it, should you need to integrate with existing pods. And we'll talk a little bit more about that shortly. All right. Our next platform. Now, this is, our 3450 LD Quantum X Photonics InfiniBand switch. It is the world's first CPO-based switch. What is CPO? Co-packaged optics. Okay, what does that mean? First, let me tell you that it's similar to the Q3400, but this allows MPO cables to plug directly into the front of panel without the need of transceivers. Okay, so this not only saves money by not having to purchase optics, which is very, very expensive, but it's easier for serviceability, and it in addition, it's just much simpler, right? We handle everything internally. All you got to do is bring your MPO cable in, plug it in, you're good. It features a hybrid liquid cooled design, enabling most of the cooling of the switch to be done with efficient direct liquid cooling technology for greater power efficiency. So here is a quick visual of what a traditional switch would be, kind of like our earlier 3400. And the co-op package optic switch that doesn't require an optics at all, so you can just plug it directly into this switch. Okay, I know I moved kind of quickly, but we are limited in time, so I'm going to jump into our Ethernet portfolio. So we also have a Spectrum X platform that I'm going to get into. But before we do that, let me go ahead and build the stage with, our current, components or Ethernet switches that we use in our AI factory in the Spectrum X platform. Because again, these platforms and these designs are not just one switch or one ASIC. It's really a symphony that takes the hardware from the network switch, from the node adapter, the Bluefield DPU, and the internal software, and puts it together and shares and makes this stuff happen, where we can actually give you 100% line rate while still maintaining the ultra low latency that's required for AI factory, AI learning, and LLMs to go ahead and train these things without impacting at all the latency or the throughput. And the only way we can really do this is we need to work very, very, very closely with all components. And this is why our AI factory is critical to have end-to-end connectivity, and that's why there's a reference architecture that kind of talks about that. But again, I'm getting a little ahead of myself, so let's go ahead and talk a little bit about these boxes here. This is our Spectrum-based Ethernet switches. We've had a larger portfolio before, but we EOL'd a lot of them because as we move forward with 400 and 800 gig, we want to focus on the latest and speed and performance, while still maintaining some of the stuff that's necessary. But we have the 2000 to kind of takes care of it. Is based on our Spectrum ASIC, but it takes care of a 1 gig. We have the SN3000. A couple of these are kind of recently EOL'd, so the SN3700 and the 3700V, you may still find them out there, and we do support them. But again, we're trying to shift people over to the 4000 and the 5000 series. But we definitely have the 3420, which is a 48 ports of 25G or 10G, and then 12 ports of 100G. That's still one of our main switches, because 25G is really popular and very highly used on the storage side. So for the 4000, we do have the 4600 and the 4700. Essentially is our Spectrum 3 ASIC, which there's tons of additional benefits as you move into the higher or newer generation ASICs, specifically in the forwarding databases, the routing tables, and a bunch of stuff, and buffers and things like that we don't have a whole lot of time to get into. But it's important to know that as we move into the newer generation, we actually put all the necessary requirements that's needed for supporting AI factory. So the 4000 series, again, we have the 800 gig and 200 gig, or 100 gig, 200 gig, and 400 gig. But the 5000 series is where we are today, which is what we offer for building any AI factory that's Ethernet based, because the 5000 series has additional hardware features that really help, and there's a lot of secret sauce in our hardware, because that's why we've been designing this stuff specifically for clustering and HPC and AI. So there's a lot of things that we do to maintain 100% line rate, so that's 800 gig per port in any direction, while still maintaining sub 500 nanosecond latency, and sometimes it's much lower than that. And we have to, in order to be able to do what we do with the AI factory. So that is usually, you can get those obviously by themselves if you really need them to build, whatever Ethernet. We, support all the layer 2, layer 3, and 4 through 7, all the stuff, standard stuff using Cumulus Linux. But primarily what we designed this thing is to work with the Spectrum X platform. So here's the Spectrum X platform. The Spectrum X platform consists of the 5000 series switch that is paired up with our SuperNICs. And in this case, the Bluefield 3. And moving forward, there will be a Bluefield 4 coming up very shortly. Because Bluefield 4 will be PCIe Gen 6 based, so we'll be able to pump out, 800 gig natively. But this particular solution here allows us to build an AI factory while not losing any of the latency and throughput or packet drop that's normally experienced with Ethernet, technologies, right? You can have a 400 or 800 gig switch from many vendors out there, but try to run at 100 gig or 100% line rate and still maintain that low latency that's required. A lot of the congestion control mechanism starts kicking in, and there's different types of congestion control mechanisms that really affect the performance. So in order to really control this, we needed to be able to pair this solution together to guarantee that that doesn't happen. All right, so let's move on to the next one. So I talked a little bit about the components of the Ethernet side of things and the Spectrum X. So let's move on to the adapters and the Bluefield and SuperNICs. And then I'll talk a little bit about optics and then turn it over to Gary. Let me, again, here is a quick, overview of our past, kind of generations of the ConnectX portfolio. The ConnectX is the adapter that we use for the different platforms that we have, right? So earlier I talked a little bit about the InfiniBand earlier in the beginning of this presentation, how, the X800 generation uses a ConnectX 8, but prior to that, we had the ConnectX 6, DX 7, and we addressed, those addressed the 50 gig, the 200 gig market, and then of course the ConnectX 7 and 8 is what we offer today with our solutions for our AI factory. One thing I forgot to mention, and I want to go ahead and say this now, is that, as we move into these new protocols and these new, intense high performance clusters and AI factories, we do move very quickly from like for example, the ConnectX 6 to the ConnectX 7, because ConnectX 7 has just a lot more, and because we do some merging of hardware features and leveraging of hardware features between the network switch and the adapter, the new ASICs allows us to do much more. So we always tend to move forward. Having said that, many of our cables tend to, you may notice that we may EOL some of the like the EDRs and HDR cables. Well, this is where our partner, Siemens comes in. We work closely with partners like Siemens to be able to offer some of these cables for you guys as we move on to the newer technology. And we may EOL something that's like an EDR that's like 100 gig or 200 gig or even 400 gig. Siemens, we work closely with Siemens to make sure that they provide the right cables, because believe it or not, cables and optics are crucial, even though people may say, well, no, you can get those cables pretty cheap anywhere. Well, there's a lot that happens between one end to the other that does error correction, right? And error retransmission. So if that is not done properly, there could be internal drops within the cable that increases the latency, and that decreases the performance. So it's important to get the right cables, which is why we have an end-to-end solution. If we can't provide a certain component in the middle, we will work with partners like Siemens to provide those things for you guys and guarantee that these cables will perform as good as the original cables that we offered. So I just wanted to point that out, because as we move forward to the new technologies, that you're going to see that, and hence why we have these kinds of webinars with Siemens to bring you this kind of information. All right, so ConnectX 4, 400 gig, ConnectX 8, or ConnectX 7 is 400 gig, ConnectX 8 is 800 gig. Let's move forward. ConnectX 8, let's talk about that, because that's essentially what we're providing now with the new AI factories and new NVL72 type offerings that we have with our super pods or /AI factories. They will come with ConnectX 8 SuperNICs. Now, this is one of our SuperNICs. Again, SuperNIC is an umbrella term that we will provide, because SuperNICs can also consist of our DPU cards, which has essentially the same ASIC. but it has more. It has ARM core processors. It's a system on a chip, and I'll talk a little bit about that. But the Connect X8, we will have different types of offerings. We will have the 200 gig per lane, one XDR OSFP version, which will be one 800 gig port. We'll have two 400 gig ports version, and we'll have two 200 gig mezzanine cards that mezzanine card is primarily made for the NVL 72 trays, GPU trays that we have. Or they're also available for our OEM partners like Supermicro, Dells, and things like that. We also will have OCP 3.0 offerings for, again, the Dells and microsystems and things like that. The Bluefield 3 portfolio. So the Super NICs also include the Bluefield 3. Now this depends because the Bluefield 3 can do it's essentially a system on a chip. It has a built-in PCI bus, switch. It has built-in memory, and it has up to 8 cores, 16 cores, ARM core processors at 2.2 gigahertz. So we'll have two different versions of Bluefield 3. The Super NIC the Bluefield 3 that we put under the Super NIC umbrella are the ones on the right, which is the B3140H, the 3220L, and the 3210L. And the reason why is because these have 8 ARM core processors at 2 gigahertz, and they can stay underneath the power budget of 75 watts because each PCI bus in a server, the standard power budget for each PCI slot is about 75 watts. So anything over that will require auxiliary power. And that's not a problem. The server vendors offer that, and so do we. We offer the cable anyway. But it becomes a little more complicated because you need to add additional power. So the Bluefield 3 that is not under the Super NIC umbrella is the one on the left, which has double the amount of ARM core processors, double the amount of everything, right? 32 gigs of DDR, and it does run above 75 watts of power, which will require auxiliary power. But we usually use these for north-south type traffic, basically all the control traffic going from north-south. And then we use the Bluefield Super NICs to do a lot of the east-west type traffic. So there's a lot of reference design. We can get really deep into this kind of stuff. But time at the currently we don't have a whole lot of time to get deep into this, but be happy to discuss this at an offline or a later time. But I just wanted to point this out that we do have Bluefield 3 that are under the Super NIC umbrella. All right, so let's talk about transceivers. When you start connecting these components, there's going to be different types of transceivers, which has become somewhat of a heartache for many people because as we move into the new technology, PAM4 200 gig SerDes that runs at 200 gig per lane. You have the QSAP-DD, you have the old QSAP. So if you can see the evolution of where the optics have, and this applies the same thing with cables and active optical cables or passive cables. You'll see the evolution, right? We started off a long time ago with 40 gig, and then as you move over, the FDR, the EDR, which is 100 gig, also Ethernet also kind of falls under the same thing, where you're running all at a 25 gig per lane NRZ, and as we move into the 200, 400, and 800 gig, things have to change a little bit. We have to get bigger transceivers, and then there was a standard out there, the QSAP-DD, that was more of a Juniper thing, but we still support it in some of our switches. So, where you have double the amount of lanes, but you're still running at 50 gig per lane. But as we move forward to support these 400 and 800 gig, we need to be able to pump a lot more data per lane. So we have to move beyond 50 gig per lane. So now we're doing, we moved on to 100 gig per lane. Now we're moving on to 200 gig per lane, and 200 gig per lane times 4. Now you can see, right? You got 800 gigs now in just 4 lanes. You double the lanes, now you got 1600 gigs. And that's how we move forwards. Now, when that happens, you have different types of transceivers that you guys need to be aware of, because when you're running at these kinds of speeds, heat becomes an issue. Thermal issues become, so we need to take all those things into account. So you'll have things like this where you have a flat, OSFP transceiver. They call it RHS, or you'll have a finned version of it, and they're pretty much identical. The difference is that one is finned and one is flat. So usually the flat ones are used for the adapters, because the adapters, their cage can only fit, this version, the flat one. The finned version is primarily used for the switch side. So when you order, or you're thinking about designing a backplane or a leaf or a cluster of any kind that will have connectivity, you need to be aware of the transceivers that are required. You're going to need, finned for the switches and flat for the nodes. All right. On the XDR side, as we move into the 200 gig per lane, one thing to be aware of, I know this is a lot of information, and where are we? I'm a little bit over my time here, so I'm going to try to speed this thing up a little bit. But the connectivity for XDR is going to be all in single mode optics and single mode transceivers. We'll have options for you, for 2 kilometers, 500 kilometers, and then some, right? So the 1.6 terabyte one is the dual port 200 gig, a dual two of the 800 gig. So if you're going to use both 800 gig ports on the XDR switch, you want to use the transceiver in the middle. So I'm sure we'll get these slides to you guys. You guys can kind of dissect this a little bit offline, but do know that the transceivers here for XDR are slightly different, and they do require a little bit more granular look into it. And we're going to be here. There's a lot of us that help. Your partners will help. Our partners and your partners will help with this to decipher which ones are needed. The old, or not old, but the 400 gig NDR. This is just a quick summary of the NDR, the stuff that we've been shipping for a while now with our AI factory or SuperPods. Again, you have the finned, the not finned. You have the ones that are meant for the switch side. You have the ones that are meant for the built-in compute ports on the H100, H200, because we have a mezzanine card in there that kind of aggregates the ports in, and so we need the flat ones on there. But then you have the blue field and the ConnectX 7 and 8 on the right-hand side. So this slide kind of will give you a picture of the type of and the part numbers of the type of transceivers that you would normally use when you're designing an NDR connectivity. Okay. So with that, I know I kind of went through it very quickly, and I apologize, but I will be available. Both Gary and I will be available to answer questions and things like that. But I'm going to hand it over to Gary Bernstein. He will cover the rest of this slide or this presentation.
Thank you, Ulysses. Good stuff there. There's a lot of information, definitely. But thanks everybody for coming again. I appreciate it. And right now I'm going to go through some of the NVIDIA recommendations and requirements for connecting all the hardware that Ulysses just covered. I'm going to first start up and kind of come up a level and talk about the typical architectures. On the left side over here, I'm showing an example of a traditional data center architecture that has been around for many years, really, with the CPU-based servers in a leaf spine architecture. This is really now referred to as the front-end architecture and the front-end network. The speeds I'm showing there are really just examples, but typical server speeds today are 10, 25, or 100 gig. The right side is really what's completely new with AI. With any AI builds, you will really have to have both the front end and the back end. Everything that Ulysses really just covered is primarily on the back end of the network. Within the back end, you have scale up and scale out networks. We're not going to get into that detail, but just for your awareness. I also am highlighting here really 4 different than the typical interconnection areas for both networks. So on the left side here, on the traditional front end, the one is just showing the switch to switch and then switch to server, and then same switch to switch and switch to node on the back end side. So now I want to zoom in a little closer on the switch to node connections. So what I'm showing here is really an example of the compute cabinets and the leaf switches in the middle connecting all the nodes together. And on the right, I really just have a close-up of a single node or server and the typical connections required. So all AI networks have really 4 different networks: compute, storage, in-band management, and out-of-band management. An 8 GPU server is the most common, so that's what I'm showing. And the green arrows here are showing 8 different connections required. This can be either InfiniBand or Ethernet based. Most commonly, these are 400 or 800 gig, as Ulysses mentioned. The red is just showing where that there's storage and in-band management connections. There are typically 1 or 2 of these each, and these are always Ethernet. Typically, it could be 100, 200, or 400 gig. And then the blue is just showing 1 out-of-band connection that's 1 gig Ethernet using copper RJ45, Cat6, or 6A. So really, you can have up to 13 total connections per node. It's a lot. Next, I really wanted to we wanted to highlight that NVIDIA does support using fiber structured cabling in their builds. Most people are not aware of this, and so really wanted to kind of go and talk through this. So I'm highlighting some of the key points directly from the NVIDIA document. As you can see here, it's the NVIDIA interconnect cabling requirements for IB and Ethernet solutions. This is additional guidance that NVIDIA provides beyond the basic guidelines in their reference architectures. Many of the builds today are using point-to-point, but we are seeing more people starting to move to structured cabling. NVIDIA released this document back in July of 2023, and they've made several updates, including the latest one in June of this year that adds 800 gig as well as XDR. So as you can see from the diagrams here, these are straight from the document, that they allow for up to 2 patch panels. So you got a trunk in the middle here, you got a panel on either side. In this case, it's showing an example using the 9700 switches Ulysses was talking about and the transceivers there. So either multi-mode or single mode. So some additional comments from NVIDIA and their documentation. You see that the structured cabling eases servicing of the transceivers, patch panels, and trunk cables add further flexibility. And really important one is the performance, that their transceivers are designed and specified to allow for and assumes up to 2 patch panels in the link. That's always a question that people have, and I don't want to go to using panels because it's not going to meet the performance requirements, but it has been designed that way. So now I wanted to show an example of where we typically see structured cabling being used. I'm showing a couple different pods here. So on the left side with the compute cabinets and a network cabinet, this is just an example of a scalable unit. Another one on the other side, and because it is required to connect all leaf switches to every spine switch between the SUs for the scale out network. Below is an example of fiber cabling that is commonly used. I'm showing a single mode example here of a bundled trunk with 128 fibers or 16 legs, MTP legs, going into patch panels on either side with the MTP adapters that's shown here. And then there would obviously be some MTP jumper cables connecting into the transceivers in the switches on both ends. Siemon offers a lot of different fiber counts that allow users to match up their port counts on the NVIDIA switches or the GPU servers, like the 128 or 64 or others. And you can see how many connections are really required, when you're building out a network like this. So now coming back to the NVIDIA cabling specs. This chart is straight from the NVIDIA document, and they do actually highlight specific performance requirements and loss levels for the connectors in order to perform properly. And it does require ultra low loss fiber connectivity in order to meet these specifications. So as you can see here, I'm highlighting in green that the Siemon performance for these particular connectors, which really exceed all the requirements that NVIDIA has. Here's one more chart that from the NVIDIA spec document that states the maximum channel limits. This is pretty important here, and really was most important for the overall performance of the system. You can see they do specify a 2 dB max insertion loss limit for both single mode and multi-mode. Again, using ultra low loss is critical, and Siemon does provide a pretty significant margin on this to make sure that everything works properly. Okay, so now I'm going to transition and show some reference architecture example designs and some cabling best practices. So this is an example of a design that Siemon did for a neocloud company that was deploying 100 H200 nodes in an air-cooled environment. So still following the NVIDIA SuperPod reference architecture, customers are using a hybrid cabling approach, meaning point-to-point for leaf to node and structured cabling between the leaf and spine switches. So I'm showing here as an example of 5 compute cabinets here with 4 nodes per cabinet and 1 network cabinet, right? That makes up 1 scalable unit. And really not every DC can handle this today, because that requires about 40 kW per cabinet for the H200. And the racks on the side over here are just representing the network cabinets for the other 4 SUs, and then the DMARC cabinets on this side. So you can see above here, we show cables. Actually, the point-to-point ones here are going from the leaf switches to the nodes. And then the cables above here, this is representing Aqua and single mode, are showing fiber trunks going to the other network cabinets and as well as the DMARC points. So we are starting to see this as a best practice from an installation standpoint. So this is just a close-up of that, so you can see a little bit closer the network cabinets and the structured cabling. You can see here we've got 8 leaf switches and 4 spine switches. These are all the 9700 that Ulysses showed earlier. On the top of the network cabinets are patch panels or enclosures with mostly MTP ports. There are some LC ports for out-of-band management and uplinks. And then the patch cords, obviously, that are going from the panels into those switches. If you weren't aware, 400 gig or NDR uses the MTP APC connector for multi-mode fiber. So this is different and not traditional. It does use a green housing here. And so you should be aware of that. It is an important difference for backend networks. So this is an example of a 256 node cluster. So it's really 2,000 GPU or 128 node clusters interconnected together. I just like showing this because it just shows how many connections that there is in a typical deployment in AI factory, as we were talking about. It's kind of crazy, really. At the bottom are the nodes in the SUs, going to the leaf switches, then to the spine switches, then to the supercore switches. So this is an example of design that Siemon did for a customer that we will be deploying some of the new hardware that Ulysses was talking about, and this is 72 nodes of XDR with the B300 as well. So it's using the new Q3400 switches, which are 1.6 terabytes, right, per port total, as well as the SN5600 800 gig switches that Ulysses was talking about, both of these. So this is using DLC, which is direct liquid cooling, with 9 nodes per cabinet. The B300 nodes are using the CX8 800 gig. as well as the Bluefield 3 400 gig NIC cards. And then you can see there's 4 different network cabinets here in the middle with the Q3400 switches on either side, and then the 5600s and the other switches are in the middle here. As Ulysses highlighted earlier, the XDR transceivers are only single mode, so the customer will use all single mode cabling for this particular use case application. So here's another use case I wanted to share with the NVIDIA NVL72 cabinet and the GB300 Ethernet GPUs. The NVL72 also uses liquid cooling, and each cabinet has 72 GPUs. This example is showing 288 GPUs in a scalable unit with one network cabinet right in the middle supporting the 4 NVL72s. Another option for cabling besides all fiber is using active copper cables or AECs for the right use cases. In this example, we're using AECs for the switch to node and fiber for the leaf to spine. The blue lines I'm showing over here are 800 gig cables going from the SN5600 to the CX8 cards in the compute trays. The light green ones here are in-band management AECs going from the 5600 to the Bluefield 3 400 gig cards. So this needs to be a breakout cable like shown over here, going from 800 gig to 400 gig, to 400 gigs as shown. We're also showing this routing with the AECs horizontally through cable managers up at the top and at the bottom, and then down or up to the compute trays. We've definitely seen, and this is in open cabinets obviously here, we've definitely seen this type of routing deployed by some customers. In addition, Open Compute is actually working on finalizing a reference design for the industry using the same routing approach. Siemon can offer these 800 gig AECs up to 7 meters in length, and just some of the benefits of using AECs are lower overall cost, lower power than the transceivers, and better reliability. The other thing I just wanted to highlight while I have it up here on the construction of the Siemon high-speed copper cables, as you can see here, these use a mesh sleeving with separate copper pairs inside here versus a single kind of stiff jacket. This provides a lot more flexibility in routing the cables. This slide just shows a summary. It's a nice summary of cabling options by length required. If you look at the cabinet here, the row of cabinets, I've got a network cabinet in the middle here and compute cabinets right all along the side. And the closest cabinets here can use DACs, for example, typically up to 3 meters. Then maybe AECs, like the example I just gave, up to 7 meters. Then maybe AOCs up to about 30 meters. And then the fiber cabling. So it really is an important parameter is understanding the layout and the length requirements. And Siemon has all of these different options available. So here I just wanted to share a summary of some of Siemens MTP patching solutions that are out there to utilize unstructured cabling like we've been talking about. On the side here are light burst patching platform enclosures or panels, 32 ports per 1U, the light burst Infinity with 48 ports per 1U, or the light stack up to 72 ports per U. These support all the NVIDIA transceivers, which currently use all MPO12 connectors. We are starting to see the industry move to a base 16, as well as a very small form factor patching solutions to increase panel density, then converting to an MPO12 8 fiber, or potentially for 800 gig DR8 transceivers that are out in the market. We're also starting to see the use of fiber shuffle boxes and cables being used for the NVL72 GB300 designs that can provide some more flexibility and efficiency in the NVIDIA multi-planar architectures on the new designs. So really just trying to now to summarize the data center solutions that Siemon manufactures, which are typically used in these DC AI data centers. Bundled trunks and fiber trunks in a variety of different fiber counts, as I mentioned, a full range of DACs, AECs, ACCs, and AOCs, from 10 gig all up to 800 gig, whether it be InfiniBand or Ethernet. As Ulysses mentioned, we do offer the EDR and the HDR as well. Our innovative LC blade patch, LC cords, copper skinny patch cords, and then the patching solutions that we had talked about. So now to just wrap up and summarize some of the key points we covered. The NVIDIA solutions really cover the full spectrum of potential use cases that are out there. Ulysses shared, their new XCR 800 gig platform that is available on the market today. Siemon has worked with many customers in their design and deployment of GPU networks over the last few years, and really has a lot of experience and can be a trusted advisor to our clients. I showed several different examples of cabling best practices that can use a combination of point-to-point fiber, structured fiber cabling, or high-speed copper cables. And since Siemon is really the only cabling manufacturer globally to be part of NVIDIA's partner program, we have been able to work closely within the NVIDIA team and collaborate to provide unique solutions for our customers. So with that, Brian, I'll come back to you if we have a little bit of time for questions.
Absolutely. Thank you both for that tremendous insight, and thank you. Appreciate that. We have had a few questions come through the questions panel. So one came in quite early, so I'm not quite sure who to direct it to, but it was framed as, can a QSFP28 transceiver work in a QSFP56 port? That was the question.
Yes, absolutely. Yeah. Yeah,
Okay.
QSFP 112, 56, 28, they're all backwards compatible.
Excellent. Thank you. And the next couple were directed for you, Ulysses. The next one was, will co-packaged optics be available for speeds below 800 Gbps?
Technically and eventually, yes. Initially, we will work with just the 800 gig because we're trying to build these AI factories that are just monster AI factories. So, the resources are focused on the maximum throughput. But from what I understand, that is a roadmap issue to be able to. And actually, to tell you the truth, there are cables and transceivers that can reduce the speed. So yes, you can go down to 400 gig and 200 gig, but with the co-packaged optics solution where you don't need transceivers, I think that's a roadmap issue or item.
Okay, thank you. The next one for you, Ulysses, was, can we expect co-packaged optics technology in nodes/GPUs in the future?
Yes, in the future, but again, that's later. Not at the moment. We don't have that, but
right.
It will.
Okay. The next one was for a specific slide you had, Ulysses. The question was, what is the difference between LACC and ACC on one of your slides?
Yeah, that's a linear active copper cables. That's new. It's the same thing as the active copper cables for NDR, but with the LACC cables, they have an integrated IC amplifier to be able to support the speed of 800 gig. So essentially, it's the same thing as the active copper cables, but with an additional amplifier in it. So it's called, linear active copper cable. We won't support passive cable because we can't, not for 800 gig. But.
Very good. Thank you, Gary. This one is for you. Is it fair to say that as we move to higher speeds, 1.6 terabyte and beyond, considering the bandwidth and distance requirements, Single mode transceivers and SM cables will be a norm. And if that is the case, is it a good design practice to consider SM cables and connectivity for deployments today to be able to migrate to higher speeds in the future?
That's a mouthful. Okay. Yeah, but I got it. Yeah. On the single mode side. So it's a fair question. As Ulysses highlighted, for them, the XDR platform is only single mode. And I mean, the reality is we've seen in general move to more single mode, but even today for NDR, I think many of the deployments has been a combination, right? It's probably a lot of it has been multi-mode down to the nodes and single mode between the switches. But as those scale out larger, we are seeing it being more single mode across the board for consistency. So would you agree, Ulysses?
Yes, I agree. Yeah, and single mode allows us not only for consistency, but it's a better way to get those speeds and latencies down.
Yeah.
Okay. The next one, and a few have popped in while we're starting the Q&A session, guys. So this next one I'm seeing, can the presenters talk about the structured cabling support using NVIDIA all optical switch? He says, I assume it would be an MPO-based patch cord approach, question mark.
I'm exactly sure, but yes, it is primarily all MPO. I mean, it is. I mean, there's some, like I said, LC for out-of-band management, for example, uplinks, that are 10 gig on the SN2201 switch, I think. But for the most part, yes, that structured cabling, and I showed some examples of that. It was all using MPO cabling, whether it's 200 gig, 400 gig, 800 gig, any of those.
Exactly. Yeah, I agree with that.
Okay. Couple more, guys, while we get a couple more minutes. Ulysses, how does NVIDIA support partners and customers in navigating the transition from traditional Ethernet to AI optimized networking like Spectrum X?
Wow, that's another mouthful. Okay, so that is interesting because we have different methods to do that, right? We have multiple teams. We work very closely with partners like Siemens and others. We rely a lot on our partners to be able to help the customers in transitions with the support on the back end from us. There's teams like myself, account managers who do a lot of the pre-sales and designing and things like that. And then we have post-sales teams and professional services that takes it way beyond that. So it really depends. It depends on what it is, the opportunity, how big, how much help, how much hand holding. But our first line of defense is our partners and the channel, right, and our OEM. And our job is to support them. But in turn, there's always some gray area there, and waters get muddy where we all kind of jump in. So we make it work for whatever the situation is. So I guess I don't know if that specifically answers the question, but we do have multiple teams to be able to handle this kind of stuff.
Oh. Thank you, Ulysses. And I'd like to just squeeze in two more, guys, before we close out. This one's for you, Gary. Gary, are you seeing more customers deploying InfiniBand or Ethernet for their compute networks?
Yeah, that's a good question. I think a lot of people are asking about that. Is it going to be IB or Ethernet? And I guess if you look, traditionally and over the last several years, it's been primarily InfiniBand, right, with NVIDIA. But we are starting to see that change. The trend of with obviously the Spectrum X platform and Ethernet, we are seeing more Ethernet. And the latest Del Oro just did updated their forecast just actually a couple of months ago, I think, that showed for the overall market was that Ethernet would overtake by volume sometime next year InfiniBand. So we are starting to see that shift a little bit, but right now it's a little bit of both, but the trend is kind of going towards more Ethernet. I don't know, Ulysses, if you have anything to add to that.
No, I think you nailed it. It is interesting though, because InfiniBand is not going anywhere because InfiniBand still beats the latency on Ethernet because, you know, it's just a much more simpler protocol, which is why we use it for ultra low latency. But with our Spectrum, like you mentioned, our Spectrum X platform, we were able to do almost the same on the Ethernet side. So we do see a lot of people saying, hey, we prefer, they feel more comfortable that way. But you know, if we're talking about 50 to 100 nanoseconds makes a big difference, then InfiniBand is always going to be your go-to, right? But you know, we're there with Ether.
Nice.
Thank you, guys. And then just the last one before we sign off here, Ulysses. How is the X800 platform switch work backwards compatible with the NDR EDR?
Yeah, so I had a slide there on that, but that is a good question because that is something that comes up all the time. That's why we came out with the 3200, the 2U that has the two switches built in. That one is meant so that you can use the NDR cables and optics and reduce the speeds to support NDR and in HDR. So this is where we do have reference architectures out there that talk a lot about this. We have people like myself and Gary that are here for pre-sales help in designing BOM creations to help with these kinds of scenarios. Normally, if you're going to invest in an AI cluster, you want to future-proof this thing and you want to go ahead and go for the best and the top. But if you need to tie into an older cluster, you definitely want to do this with the Q3200. So there is options and solutions for that. No problem.
Awesome. Well, guys, we are 2 minutes over time now. We have seen a bunch more questions come in. We will get the experts to respond to your guys' questions offline, but we're going to go ahead and close out. And in order to, I'm going to say, I want to extend a big thank you to everyone who joined us today and to Gary and Ulysses for sharing their expertise and insights. If you'd like more information on how Siemon and NVIDIA can support your AI data center initiatives, please reach out to our presenters directly or contact your local Siemon or NVIDIA representative. So I want to thanks again for everyone who attended, and we look forward to seeing you at our next Tech Talk. Until then, take care, everyone, and enjoy the rest of your day.
Thanks, everybody. Appreciate for joining us.
All right. Thank you, guys.